How are you doing?
So,
Fine, sir.
Okay. So, how was your exams? Shoaib?
Alhamdulillah, it was okay, sir.
Okay, so what was the syllabus?
Syllabus, it was like the human eye and light.
Okay. So, what is different? So, did you answer all the questions?
Yes, sir.
Do you have any doubt?
No, sir.
Oh, that's good. So, Govita is looking for what is the definition of resistance.
I got
You got?
yes.
Okay, that's good. What is difference between series and parallel combination of resistance? They might ask such question. Okay.
So we are not having resistance in series and parallel.
Why it's not in syllabus? Oh, it's class 10th, na? So why not? Why
But
not? Hmm?
but a half is there.
A half is there. Okay. Then you are saved. So what we studied in this chapter, effect of electric current, magnetic effect of electric current. So will you summarize what we studied, Shoaib?
Yes, sir.
Will you brief what we studied in this chapter, magnetic effect of electric current? Will you give little summary?
It's like that electricity also possesses magnetic effects.
Yeah.
Yeah, and the thumb rule.
Yes. What is thumb rule? That's the right hand thumb rule.
Uh,
Right hand
uh,
thumb rule. What
right
is
hand
it?
thumb rule.
What is it
Uh,
used?
to find the like which direction the north and south. Wait.
Which direction is the direction of electric field?
Yeah.
If the direction of current in conductor is given, right?
Yes.
So if it is a straight wire, so how will be the direction of magnetic field?
Yes, sir.
If the conducting wire is a straight line, okay, so how we will define how we will get the direction of magnetic field?
By which direction it's flowing, the current is
Yeah.
flowing.
Yeah, how we will do that?
You should use the right thumb rule.
Okay, that's good. So do you have any confusion?
No, sir.
Okay. So it is well studied that whenever a current is passing through a conductor, okay, it generates magnetic field. Okay. When we bring another magnet in the vicinity of current carrying wire, that magnet get effects of the magnetic field generated by the current carrying conductor. That was the experiment of that, what can I say, campus needle one, right? Do you remember what was the compass needle experiment?
Yes.
Okay. So these two are interrelated. So it is being said that if there is a magnetic field, the motion of is the magnetic field, and we will make motion of a conductor, okay, or conductor is stationary, and we will make the motion of magnets, then there will be a electricity in the conducting wire, right? So reverse is also possible. Today we have to discuss few concepts. We already calculated or got the idea of magnetic field due to a straight or curved wire. Okay, there is no doubt, I think. Now we have a solenoid. Okay. Have you seen when in the electronic device, nowadays guys are not playing with devices. Okay. The mobile phone is so compact that you can't open. In early days, people used to see the radios, transistor, but transistor is not in the use. So in transistor, you might have find n number of electric components. So one of the components you might have seen that, suppose this is a rod, okay, and you have seen that this is being wrapped by a closely packed copper wire. Why? Have you seen such apparatus? Have you seen such apparatus, Shoaib?
Yes, sir.
Have you seen such apparatus?
No.
You never saw. Okay, no problem. So such apparatus is called solenoid. These are the circular coils. These are the circular coils wrapped over a metallic surface or metallic rod. Okay, I don't know what is happening. Hope this time it stays. Not staying. I don't know. This. So this is the picture of solenoid. Sorry, I tried a lot, but I couldn't. So you might have find that there are n number of turns, right? So this turns also work as a magnet. Okay. So outside we have conducting wires. Do you have any idea what is happening with me? Why this is happening? So finally, I'm sorry. This type of arrangement is called what? Solenoids. So we are seeing that this ends is being connected to the battery, right? So as the current is being established in the wire, so it will be magnetized, okay, and so it will behave like a straight magnet. Sorry, a bar magnets. The direction of field will be as usual to the bar magnet. Okay, the field will be direction of field will be going from one side to another side. Clear? As it goes in a bar magnet. So this is the definition of solenoid: a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called solenoid. Clear? What is solenoid? And magnetic field inside a solenoid. So we usually denote magnetic field by B. So today I am going to write the magnetic field due to a solenoid. Suppose this is a large solenoid. Okay, this will be equal to solenoid of n turns. N turns, turns equal to n. My God, what I'm doing. N turns, L is length. Okay, so B will be given as mu naught total number of turn divided by the length of solenoid and the current flowing through it. The current flowing through this solenoid is I and length is L and the number of turn is N. So directly remember, I saw somewhere in numericals, even in class 10th, they are asking about the magnetic field. So that's why I'm directly writing the field due to a solenoid, B due to a solenoid, long solenoid, magnetic field inside a long solenoid, long solenoid. Solenoid of length L and N TURNS turns. Did you get the meaning? So now we can write it again further, mu naught small n I. Okay, where n is number of turn per unit length. Okay, number of turns n and current I. Clear? This is just to remember. Shab,
Yes, sir.
this concept is clear?
Yes, sir.
Okay, the same way as the current magnetic field is being induced by the straight wire, the circular wire also or the loop also generates the magnetic field. But when it is arranged in some particular way, we say it a solenoid. Clear? So now I will be writing the magnetic field. Okay, I will be writing the magnetic field for a straight wire as well. So just keep these terms in mind. Okay, it may be useful. Magnetic field, magnetic field, that is B due to a STRAIGHT straight long wire, okay, and current flowing through it, flowing through it is I at distance R. So what will be its relation? Actually, I found in some questions for your standard that they are asking about the magnetic field. So this is the wire and current I is flowing through it. And we have to find the magnetic field at point P which is R separated, okay, which is R separated. So it will be B is will be mu naught I over 2 pi d. Now let's discuss what is pi. What is pi? Will you say me pi is what? Pi is 3.142. I will simply say that this is constant. We all know that pi is constant and mu naught is also constant. Clear? Gavita,
Yes, sir.
this definition is clear?
Yes, sir.
Okay. Actually, I saw when I was looking for some questions for your assignments, I saw there was some question based on these. So maybe in some way you may use it. So this was the magnetic field due to a solenoid, and this is a magnetic field for a straight wire. Now it's time to see it for a circular wire at the center. So where should I write? Will you first note it down? Kindly note it down. Clear? Should I move? Shab, are you back? Shab?
Yes, sir.
Okay, so this 2 point is clear?
Can you like explain again, sir?
Okay, no problem. I'm going to explain from solenoid. Okay. You know that this is solenoid. As we pass the current, okay, so current will produce a magnetic field, right? So this is the magnetic field, value of magnetic field inside a conductor, the magnetic field inside a long solenoid of length L. So suppose it has length L, right? And total number of turn is N, capital N. So I have written N is the turn, L is the length. And current I is passing through it, as I mentioned over. So if we will try to write the magnetic field inside the conductor, we will get this formula mu naught Ni over L. Clear? Where mu is a constant, where mu naught is constant, it has some finite value. Okay, so leave it for example for right now. And N is the total number of turns. Suppose it has 1, 2, 3, 4, 5, 6, 7, 8, 9 turns. Okay. And L is the length and I is the current flowing through it. So further we can write it as mu naught small ni, where a small n is number of turn per unit length. Clear? Babita, clear?
Yes, sir.
Shab, clear?
Yes, sir.
Any doubt?
No, sir.
Okay. So now move on to a straight wire. As we calculated that if the current is in particular direction, the magnetic field will be curling around this wire, right? Like this. Like this. So at every radius, this is the radius where D is the radius. I have written it D. So my apology. I will write it as R. As I said that distance R, so I will be writing it R. we will write it as R. Clear? So we know that every circle has particular radius from the wire. It is perpendicular distance. So it will be mu naught I upon 2 pi r. We know that pi is constant, mu is constant. Clear? Is clear or not? Shoaib, it's clear or not?
Yes, sir.
Govita, is clear or not?
Yes, sir.
Okay, now I'm going to ask you one question. Do we have a space? I'm making it over here. Okay, no problem. So suppose this is a straight wire. The current value is I, and we have 2 points, A and B. Clear? Or we say small a or a small b. So will you tell me magnetic field B at A, fill it with X, this sign, greater than, smaller than, this smaller than, greater than, and equal than, to the magnetic field at point at B. Question is clear? Okay, tell me what will be among these three in the box.
Sir, can you please explain the question?
Okay, question is that this is a straight wire. Okay, current is I. So there will be magnetic field around it. So we have 2 points, A and B. And I'm asking what will be the value of magnetic field at point A and point B in relation with smaller than, greater than, and equal. So whatever the suitable symbol will be, let me know what you will put inside this box. Question is clear? Question is clear? Okay, so tell me. Greater than. Okay, good. Will you explain why, Shoaib?
Point A is more nearer to the current.
Okay, so that's B is mu naught I over 2 pi r. So when r is small, it is reciprocal. If r is small, so B will be large. So B will be large, right? Babita, did you get it?
Yes, sir.
Did you get the answer?
Yes, sir.
Did you get the logic as well? Did you get the logic or not?
Yes, sir.
You got the logic. Clear? Okay,
Yes.
that's good. That's good. That's good. Good enough. Okay, so I will frame another question. The current is like this. Again, and this is suppose 1 centimeter this side and 1 centimeter this side. This is point A and this is point B. Now tell me again the B at A, this box, and B at B. Same, smaller than, greater than, greater than, smaller than, and equal. So tell me, Babita, what will be the answer?
So can you please explain the question?
Question explain karna hai. Okay. My question is, this is again the current carrying wire. Okay. The current value is I, and we have 2 points A and B. We have to calculate the magnetic field at these 2 points and tell that magnetic field at A and magnetic field at B, which of 3 option will be suitable for this? Fill in the blanks.
So both will be equal.
Both will be equal, right? Because the separation from the line is equal. So, okay. So tell me one more thing. Are you very well aware of vectors now? We have studied vector a lot. You all know the vectors. I'm removing this part. You all know the vectors or not?
Yes, sir.
So what I will ask now, so this is the following question. Be at a vector. This will be the direction, fill in the blanks, and this will be the B at B with vector. Now, how you will respond to this question? Crab, did you get any idea? The only thing is that vector has magnitude and direction both. Clear? That's we are studying from class 9. Vector has direction and magnitude both. So this part on the right left hand side, I only asked the scalar, so you given the magnitude equal. Now I have asked about the vector. Now see how you are utilizing your concepts.
Sir, can you please give the answer?
I'm waiting for Schwab, then I'll give you hints. Okay.
Okay,
I,
sir.
I also don't understand that part, so.
Okay. So what is the vector? Vector is actually, it has direction and magnitude both. So on the left hand side, you already answer about the direction because, sorry, magnitude. The magnitude of both is same. Now we have to tell about the directions. So when I will hold the pen in like in this hand like this, so it is coming this side, this is going this side. This is true or not? You try to see yourself and let me know it is true or not. Verify, verify. Verify this dot and cross. Just this is the direction of current. So right hand thumb rule. So if the thumb is in direction of current, then If you will curl the finger, it will give you the direction of magnetic field. So at the left side, it is coming out of paper. Okay. And on the right side is going to inside the paper. One is coming and one it is going. This is clear or not?
Yes, sir.
Ravita, it's clear?
Yes, sir.
So coming outside, coming out of paper, we will take positive. This will be positive. And going inside, it will be negative, right? Clear?
Yes, sir.
So BA, that is positive, and we'll say that vector BA, vector BA is positive, and vector BB is negative. So I have written it like that. So now I put a box. You all agree with what I have written, positive and negative? Do you agree with this or not?
Yes, sir.
Okay, now put what will be the value in this box. Positive is greater, right? If we will see, say positive is greater. Positive is greater with respect to negative, na? Greater than, of course. Govita, positive is greater than negative, na?
Yes, sir.
So what sign it will take?
Uh, A is greater than B.
Of course, good. So moving on to next concept. Moving on to new concept. Let I have some, I think, what? First, I'll stop this, I think, then. I have a short video for you guys. This is the short video. Okay, let me run this video. This is video of someone else. Okay, so let me run it first and I'll show you.
फोर्स लगेगा तो इसमें डिफ्लेक्शन आना चाहिए। स्विच ऑन करते हैं, स्विच ऑफ करता हूं, फिर से एक बार ऑन करके देखते हैं।
Did you get anything? Babita, Shrab, did you observe anything?
Yes, sir.
What? What did you observe?
When the switch is on,
Now we are coming to our point, okay? We are coming to our point. What is? Should I remove all this or will you take a screenshot? Kavita, Chef, screenshot?
I took it, sir.
Okay, Kavita, you take. And let me know.
Done.
Done. So if done, then I will explain why I shown you that video. So it is being said that I'm repeating this statement again and again. The current carrying wire produces magnetic field, right? So this was a current, the video demonstrating this experiment. So this was the wire. So let me, can you all got the idea? This was the wire, okay? and this was a magnet. When the switch was on, this magnet was getting deflected. This was the idea. Clear? When we switch on, let me explain it a little bit again. This is a horse type magnet, right? And we are passing one current carrying wire. So let me make it with red color. This is a current carrying wire. Okay. What I'll do now, I will try to fix it in some way and will connect it with a source, with a battery or whatever it is. This is source. And we will put a switch over here. And here we will again connect this with a battery. So this is the magnet and this is a current carrying wire. So if this is aluminum wire, suppose, so aluminum won't be attracted by the magnet. Okay. When the circuit is off, as we will on the circuit, the current will pass through this aluminum and aluminum will produce a magnetic field. So there is always a magnet, also a magnetic field, magnet that is producing magnetic field, and this current carrying aluminum will generate the magnetic field. Okay, so now there is two magnet field, one by this horse magnet and another by the passing the current. So now it will get deflected. Clear? Did you get anything?
Yes, sir.
So if we will reverse the direction, okay. So earlier, if it is deflected inside, now it will be deflected back, right? So if we will change the direction of current, the polarity will change. Clear? Now, if we will change the direction of magnet or polarity of magnet as well, then it will be different phenomena. So this is being called the magnetic force on a current carrying wire. Concept is clear? Can you write it in your own words? If you can't, this is the piece from NCERT book. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exert a force on a magnet placed near the victini of conductor. Just write all the sentences. French scientist Andre Marie Ampere in this year, write this as well, suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. The force due to the magnet field acting on the current carrying conductor can be demonstrated through the following activity. That experiment was the activity. Clear? Got the concept or not?
Yes.
Fab, got the concept?
Yes, sir.
Take the screenshot. Now we are moving further to see how to define the direction that wire was moving now. So how it is moved, we can also demonstrate that. To demonstrate that, we will use right hand circular axis or Cartesian axis. This is X, this is Y. So I'm rotating my hand like this. This is Y, this is X. So thumb will give you the Z direction. Okay. Thumb will give you Z direction. So how we will take? We are going in counterclockwise. So as we will move counterclockwise, that it will come out of surface. So it is says that these all are perpendicular. If magnetic field magnetic field. Magnetic field F. Field and current that is I. If magnetic field is in this direction, and current I is in this direction, then force will be toward the thumb. Got the point? Force will be toward the thumb. This is called Fleming left hand rule. This is called Fleming left hand rule. This is called left hand rule. Left hand rule. Now, to understand this well, take the left hand. Okay? And suppose the first finger is in direction of field. And this center finger is in direction of current. So these two, keep these two perpendicular to each other. Okay, these are perpendicular to each other. So what was the direction of field? That was the bar magnet, horse magnet, north and south pole. So suppose the field is in this direction and the current is in this direction. So the force on that metal chip or metal plate will be in the direction of thumb. Did you get it? Dear student, did you get it?
Yes.
Concept is clear?
Yes.
So will you tell me, Babita, Govita? Sorry, I always say you, Babita versus Govita. So will you tell me what is the Fleming left hand thumb rule? What is Fleming left hand thumb rule? It denotes the three dimensions, x, y, z directions. Okay. So if field is in this direction, or force is in this direction, and field is in this direction, the current, force will be in the direction of thumb, or just rotate. But these two will be in the anti-cyclic order. Make this is along the force, this is along the field. So this, if you will see now, if you will see that's rotate in anti-clockwise direction as we open the screw. So you will get that it is coming toward the thumb. Clear? Clear or not?
Yes, sir.
Schwab, did you get any notion or idea? Did you get any notion and idea?
Yes, sir.
Okay. So this is simple. So will you write it in your own word? What is Fleming's left hand rule? Last time, or one more time. If Fleming's rule says that if the direction of force or direction of current is along the, what this is called the center finger, and this is called the first finger, this is called the thumb. So if the direction of current is along the center finger, and the direction of field is along the first finger, then the direction of force will be along the thumb. This is what the Fleming left rule. Should I repeat it or it's okay? Shoaib, is okay or should I repeat it again?
And I understood it, sir.
Okay, that's good. Ravita? Did you understand it? Gobita, did you understand it? Maybe her mic is not working. So what is use of all these Fleming's rules? The use of it. We will use it in electric motor. Electric motor, DC generator as well, in generator, GENERATOR, in generator. How we use this, we will be reading in the next class. See, this is two magnets. This is North Pole, this is South Pole. You may keep this magnet like this, so it will be good to understand. Okay, and there will be one coil. Okay, and this is like this. This is like this, and it will be rotating within this magnets. So as the magnetic flux will change, so we will have to arrange how the direction of current will come, how the force will. So in electric motor, generator, loudspeakers, speakers, microphones. These are being used. This principle is being used in these devices to adjust the parameters. Clear? Now, if you have book, you have a question example number 13.2. Do you have books? I forget to put this. So by the way, I will give this question in assignments. This is exemplar. So try to solve it and understand it, right? Clear? Any doubt?
No, sir.
No. So you may ask anything related to today's class. Did you understand everything? Or do you have any idea? Because this is not the appropriate time to start the electric motor. Okay, it will take almost one class. So we will be doing in the next class, right?
Yes, sir.
So have some bit discussion. Tell me what is any doubt in this chapter. We'll try to solve it or we'll discuss it again. Ask some question or doubt. You don't have any question, any doubt? Oh my gosh, why? Why? So one thing I didn't told you actually, we only given you the magnetic field for a straight wire or solenoid, but I didn't given you the formula for the magnetic field due to a circular wire. So now let it. Magnetic field due to a circular wire of radius r and current I is flowing through it. Take. Then the magnetic field at the center of circular loop. Circular loop. This is the circular loop, right? So we have to find the magnetic field, and this has the radius r. So magnetic field at center. So B will be mu naught I over mu naught I over 2 pi r. Let me give 1 second. Give me 1 second. I is out. Just it went off my mind. I got confused. So confusion should be removed. So I am with books. So it is mu naught I over 2 pi r for straight wire and mu naught I. Mu naught I over A. Okay. Uh, mm, 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 mm. Mu naught I over. Okay. 2a. What is a? Where mu is again constant. Mu is constant. And a is radius. A is radius. Jo at it is written radius of circular loop. Clear? This is again here you will find it is 1 over a. Mu naught I over 2a or 2d a. So this is the case for a circular wire or circular loop. Clear? Did you understand it or not? This is just a formula you have to keep in mind. Clear? Mu naught I over 2d 2a. So Fab is clear. This formula is clear.
Yes, sir.
Take the screenshot, or if you want to write it. Govita.
Yes,
So
sir.
now I'm going to close this class. We'll meet in next class with electric motor. Till now, you revise the chapter or make the appropriate notes, right?